The internet does not live in the cloud. It lies on the ocean floor. Every day, messages, bank payments, cloud apps, video calls, military signals, and financial data move through fiber-optic cables stretched across the seabed. The Internet Society estimates that submarine cables carry around 97 to 98% of the world's intercontinental internet traffic. And in a few narrow places, that invisible system gets squeezed through shallow waters, landing stations, and corridors most people will never see. When one route fails, the world does not always go dark. Payments slow down, cloud apps lag, video calls freeze, trading systems reroute. So why does the system that carries almost everything depend on fragile cables lying across the bottom of the sea? To understand the risk, make the internet physical. A message may leave your phone wirelessly, but quickly enters fiber lines, data centers, exchange points, cable landing stations, and then the ocean. Telegeography's 2025 map shows 597 cable systems and 1,712 landings active or under construction, with more than 1.5 million kilometers of submarine cable expected in service globally by early 2026. Inside those cables, data travels as pulses of light through glass fibers. In deep ocean, the cable can be surprisingly small. Near shore, it is armored because shallow water is where danger increases. Satellites matter, but they are not the backbone of international capacity. The global internet is mostly not above us. It is below us. Cable failures are not rare. They are part of how the system works. The Internet Society says cable disruptions happen around 200 times per year, usually from natural events, phishing, anchoring, or human error rather than hostile action. Telegeography says phishing and anchoring account for roughly 2/3 of faults. That is why the internet is built with redundancy. When one cable fails, traffic can often move through another cable. Networks reroute. Operators shift capacity. Repair ships are dispatched. But rerouting is not normal service. If the fastest path is damaged, data may take a longer path. If multiple cables fail in one region, capacity tightens. If repair crews cannot reach the damage quickly, a temporary fault becomes a bottleneck. The danger is not always blackout. It is degradation. Latency, congestion, unreliable cloud services, and less spare capacity for the next shock. The most vulnerable places are not always in the deep ocean. In deep water, cables are harder to reach, harder to damage accidentally, and harder to interfere with. Rand argues that deliberate deep-water sabotage is technically difficult and requires specialist equipment. The sharper vulnerability is closer to land. That is where cables enter shallow water, cross busy shipping areas, approach beaches, and connect to landing stations. Rand describes this shore zone as the place where the threat is most acute. A cable is not just a line across a map. It needs landings, permits, security, power, backhaul, repair access, and political stability. That is where the map starts to look dangerous. Some regions are dependent on corridors, narrow paths where many cables run close together because geography, distance, permitting, and cost push them through the same place. The internet looks decentralized on screen. On the seabed, parts of it still narrow into chokepoints. One of the most important of those chokepoints sits around Egypt and the Red Sea. This corridor matters because it offers the shortest digital path between Europe and Asia. Instead of routing traffic around Africa, cables cross Egypt between the Mediterranean and the Red Sea, then continue toward the Middle East, Africa, and Asia. Size describes Egypt as a keystone of global communications. Its case study says Egypt's cable concentration carries approximately 17% of global internet traffic, and that more than 90% of Europe-Asia communications travel through Egypt into subsea systems in the Red Sea. That is why the most vulnerable place on the internet is not just a title. Size argues that no other telecom cable route condenses so many cables through similar successive bottlenecks. Recent disruptions show why this matters. In March 2024, Red Sea cable cuts severed multiple systems and disrupted an estimated 25% of telecommunications traffic between Asia, Europe, and Africa, according to Size. In September 2025, Red Sea cable damage degraded connectivity across parts of the Middle East and Asia, with reports of latency affecting cloud services. the world did not go dark. It became slower, more congested, and more dependent on backup routes. This is where the story becomes more complicated than sabotage. Undersea cables can be targeted, and governments increasingly worry about them. But many damaging incidents are not cinematic attacks. They are anchors, fishing gear, storms, earthquakes, or ships operating in crowded waters. In 2025, reporting on Red Sea cable disruptions cited experts who said commercial shipping was the likely cause. The International Cable Protection Committee noted that 15 submarine cables passed through the narrow Bab el-Mandeb Strait, and AP reporting said at least 10 nations were affected by regional degradation. That changes the threat model. The internet is not only vulnerable to an enemy with a plan, it is also vulnerable to ordinary maritime activity in extraordinary places. Conflict zones, congested straits, shallow approaches, and regions where repair crews cannot move freely. A cable can be cut in minutes. Repairing it takes far longer. A vessel must be available. Permissions, weather, and conflict can delay access. If several cables fail close together, every remaining path carries more traffic. The system is resilient until too many pressures arrive in the same place at the same time. The solution is not to abandon undersea cables. There is no satellite replacement for the capacity they provide at global scale. The solution is resilience. That means geographic diversity, more landing stations, better shallow water protection, faster repair permissions, clearer monitoring, and backup routes ready before a crisis begins. The ITU and the International Cable Protection Committee's 2025 summit focused on faster deployment and repair, better risk monitoring, and geographic diversity for submarine cable infrastructure. But resilience is expensive, political, and slow. A cable route is shaped by seabed geography, distance, landing rights, security, financing, and the willingness of countries to host infrastructure others depend on. That is why the internet's future is not only about faster chips, bigger data centers, or more powerful AI. It is also about beaches, ships, permits, sea lanes, and the narrow places where cables come ashore. The internet feels